How do neural networks use embodied robot intelligence? Imagine a robot that not only follows commands but also learns from its own experiences and adapts to new situations. That's the power of embodied robot intelligence driven by neural networks. Neural networks are computer models inspired by how our brains process information. They take in data from sensors like cameras, touch sensors, or microphones, and then decide what actions to take. When used in robots, neural networks don't just process data in isolation. They work closely with the robot's body and environment. This creates a loop where the robot perceives, acts, and learns all at once. In embodied robotics, neural networks help robots understand their own bodies through a process called proprioception. This means they know where their limbs are and how they are moving. They also interpret external signals, called exteroception, like visual or tactile information from the environment. This combined awareness allows robots to perform complex tasks like navigating uneven terrain or manipulating objects with precision. A special type of neural network called spiking neural networks mimics how biological neurons communicate through spikes or pulses. These networks are especially useful because they process sensory signals in real time and use less power. This makes them ideal for robots that need to react quickly and efficiently. For example, a robot with spiking neural networks can detect obstacles, decide how to avoid them, and adjust its movement instantly. Active perception is another key idea. Instead of passively analyzing images or sounds, robots use their neural networks to move sensors around. They might turn a camera or extend a tactile sensor to explore an object better. This sensory-motor coordination helps the robot gather richer data and make smarter decisions. Neural networks also enable robots to learn from experience through a process called plasticity. This means they can change how their connections work based on what they sense and do. If a robot tries to pick up a fragile object and succeeds, it remembers how to handle similar objects better next time. If it bumps into something, it learns to avoid that obstacle in the future. This ability to adapt without needing new programming makes robots more flexible and capable of handling new environments. Practical uses include autonomous navigation, where neural networks process sensory inputs to plan paths around obstacles. In manipulation tasks, they help robots adjust their grip and movements based on tactile feedback. Social robots use neural networks to interpret human gestures and respond naturally, making interactions smoother. Neuromorphic hardware, which mimics neural processes in physical chips, allows robots to operate with low power while performing complex tasks in real time. In short, neural networks connect perception, action, and learning in robots' bodies and environments. They turn simple machines into adaptable, self-aware systems that can explore, manipulate, and interact with the world around them. This approach pushes robotics toward more autonomous and versatile machines that can handle real-world challenges with ease.